Is a senior staff engineer at Qualcomm in New Jersey, United States. Before, he was actually here in France, in École Normale Supérieure Paris. He has a background on mathematics with a good mix of theoretical and applied research, and with a special interest for stochastic processes and application, probability, and statistics. So the floor is yours. Please start with your presentation.
Thank you. Could you please confirm if you can see my screen now?
Yeah, we do.
Okay, great. Thank you. So thank you for the nice and great introduction. My name is Tien Viet. So I have been with Qualcomm Technology from 2014.
Sorry to interrupt you. We see the wrong let's say we see not the presentation mode.
Presenter side, yeah, right.
Yes.
The slide. Oh, okay.
We see
so
the
can you see it now? Oh, I'm just sharing the whole screen, so I'm not sure if you can. Oh, okay. Let me see. Duplicate sector. Is this the one?
Yes.
Looks better. Perfect.
Okay. Thank you. So in summary, from 2014, I have been working on the development and standardization of C-V2X. So that's why in this talk, obviously, I would like to talk to you about C-V2X, obviously. So in a nutshell, C-V2X is just a solution to enable device directly talk to device, which here the device can be either a vehicle, some infrastructure like a street light or pedestrian on the road. In some extreme case, you can say, okay, that can also include vehicle talking to base station. But that, in my view, is more like a normal cellular communication. But that's just my personal view. But then that is the whole system. Maybe we can skip this slide for a moment because I would like to come to this. So this is with that vision in mind. This is how we see the architecture of the V2X communication look like. So you're going to have cycling communication here in the dark blue line that connect the RSU and the vehicle, and the RSU and the pedestrian, the people who's riding a bike, which is called the VRU, like vulnerable road user. And then you can have the UU, the cellular connection link from the base, from the RSU to the base station, for example. And then all that creates a very densely connected environment where a lot of application can run on top of that and provide a safety benefit and more how to say, enhanced transportation experience for everybody. And here, what is not, maybe what is not so very big in this screen is this little brain here in the RSU, which we call the Edge AI. So this is another vision of Qualcomm is that now every device, every connected device will be very intelligent. In this case, this will be RSU, that it will be equipped with AI and machine learning capable processor that allow those processing that nowadays is doing in central cloud or is being moved to the edge cloud that is a bit closer to the UE, to the user, to right there where the user are. And that could bring extra benefit, like this can provide lower latency, or the most important part is that this can enable efficient use of bandwidth. Like you don't need to have this transmission back and forth of all the data that need to use for all the inference work. Right. Oh, by the way, so when I'm presenting, if you have any questions, please feel free to interrupt me and ask right away. So you don't have to wait until the end of the presentation. Okay. Then just a bit of timeline on how the C-V2X technology development look like. So we have the spec, the release 7.14 spec finalized in March 2017. And by September 2017, we have the first CV2X chipset introduced, which we call this MDM 9150 chips. And by April 2015, we already have the first multi-OEM demo, which involved Ford and Audi. By October 2019, there's already a showcase of commercial readiness for CV2X direct communication in China. So basically, China is, took the initiative to deploy CV2X. And then in November 2019, we did CAM congestion control scenario testing by OEM consortium. And also at the same time, we did the live demo that shows how CV2X is ready as a market reality. So it's the first time where we have a demo that shows CV2X device in a large scale, basically. Then in December 2020, we have first commercial vehicle launch with Qualcomm CV2X solution. And in November 2020, then, as you know, FCC assigned 30 megahertz in 5.9 gigahertz spectrum to CV2X. So this slide maybe is something new for the communication community, but it's not something new for someone who worked on V2X communication. Is that normally for communication, when we do cellular, for example, when the work finish at 3GPP, right, and then the rest is like on the hand of the operator and maybe the regulator. But here it's because it's cycling, so you need there's no one in the middle to organize all this. So someone has to, take the role to make sure that all the devices are able to work in harmony with each other, which means that you have to define a use case, you provide interoperability, which means like provide a same set of parameters that all the devices are configured with, and then specifying some minimum requirements to make sure that any car that put on the road with CV2X unit, it has to be at least good enough so that it doesn't cause any trouble to other car on the road. So we have been doing all that, and now, then let's say at high level, let's say if we do all that work, then who's going to benefit from all of this? Obviously, it's the public. Public safety is the first, and maybe for the township, all the public entity that have the road run through it, also see the benefit that traffic is going through faster, and for people who is traveling on the road, there will be less traffic, there will be less accident, and everybody will be happier, right? But there's also provide extra benefit to the driver, so to say, right? Now with smart car and everything, car becomes smarter, a lot of electronic on board, then you can benefit from extra information. Like every time when you have a computational device, then having the communication going with it always provide extra benefit. Sorry about this. Like in this case, you can have map pre-trip planning, you can have automatic parking service and so on. And then there's also benefit to, let's say, commercial player, like the road operator. They can do better traffic management. To transportation logistic company, they can do better job at managing their fleet, for example. And we may have a little bit more on that on next slides. For example, here in one use case, you can have a fleet of trucks. And then for trucks, one of the things that we learn is that the ability to monitor the driver performance is very crucial for those companies. And that having, let's say, a V2X communication can greatly benefit that at the minimum cost, in the sense that now you can, all those information, right? They're not delay sensitive, in the sense that you can store the information, and once a while you come into range of some RSU, then you can upload the data, and that's it. And that's exactly what is we're trying to show here, where we have an RSU here at this part, and then as a truck full by, all the information go up and go back to a central processing center to do all this monitoring. Right. And then, of course, there come the vulnerable road user, where pedestrian, cyclists, they sort of currently experience high fatality rate and high accident rate. Now, let's say if we can somehow enable the phone to be able to talk to the car, and then having an application that notify the car about the presence of the VRU, then that can also greatly benefit everyone. Right. So basically, this slide sort of recap all of these, basically 4 components of V2X communication: V2I, V2V, V2P, and V2N. Right. So then, with Qualcomm, we are continuing to work on that direction to deliver the V2X technology to the community. And next, I would like to show you what we have been doing so far, let's say in this year, to realize that vision, which is encapsulated in the 3 use cases. We have the cycling positioning. So as you know, in order to have an effective vehicle, V2X, how to say, effective transportation application, knowing the position of the car is very important. And in some cases, you don't see that happening. And then it's become crucial that we enhance that positioning so that the service is delivered to everybody. Then we have another use case where we have some smart RSU that provides smart information to everyone, connecting to the network. And then we will see more of that in the next. Actually, I make a mistake about the slides. So actually, I want to talk about this slide. Sorry. Let me see. Oh, no, I think. Wait a minute. Yes, so this is the one. So we have three use cases. We have the first use case is for GPS positioning, where if you are ever in this situation, then you would really appreciate this. Let's say when you are driving happily on the road, and you come into a very busy intersection. Let's say some roads is merging to the highway, and then there's an overhead road that sort of block the GPS signal. And then you are ready to make a turn to exit the highway, but suddenly the GPS signal is lost, and then your map is freezing, and then you don't know if you are making the right turn or not, and then you miss a turn. That happened to me a lot. Right? And then also maybe sometimes the map keep rotating because now the location is lost, and then the app is confused. What is the orientation of the car, right? Then in the first use case, we have this RSU that provide augmented positioning signal to the car so that the car can still accurately track its position, even though if the GNSS signal is lost. And then that could greatly benefit the scenario that I have just discussed before. So we're going to see a video about that in a moment. The second scenario that we look at is about the radar. So radar is great, right? We have seen some talk by other presenter yesterday. Radar is great. Like it can provide you information about not the position of the car, of the other car, but also the velocity and heading of those cars. Now, is that radar start become a problem when everyone have radars, basically. Now, if everyone have radars, then someone who is very close to you can also turn on his radar, and then his radar gonna illuminate your radar receiver and probably block your radar receiver, and then your radar is not working anymore. All right, so we will start looking at that. And then the last use case is somewhat similar and connected to what we have seen in the last talk, is where we have a smart RSU that provide extra safety benefit to other vehicle on the road. Now, the thing that I really like about this RSU is that it's not a big one. It's just a small box on top of the street lamp, but it's contain everything. It's contain a communication feature, how to say, the communication capability, and also the smart and machine learning capability to do a smart RSU road. So we will also see that. Okay, so with that, if there's no question on the floor, I would like to proceed to show you the video of the demonstration. Okay, so maybe we start with the enhancing safety with smart RSU. Okay, so here, this is real-time demo with OTA communication. So we see on this is the drone view of our headquarters in San Diego, where this is the main building, and on the left-hand side you have a parking lot, and then we have an Eagle vehicle that is coming out of the campus, and its intention is that come and merge to the main road. So this is the video view from the point of view of the driver of the vehicle. Now, in the vehicle, we have a display to running sort of navigation application, which is basically high definition map with some enhancing information that is that the vehicle is receiving from the RSU. Like, for example, here in the map, you can see this is the location of the RSU, and then this is the location of the vehicle. So basically the RSU and the vehicle, they are both equipped with V2X commercial devices, and they are doing standardized V2X communication, including the format of the packets. So we are using the same format. It's defined in SAE for detected object sharing in this demo. So it's basically equivalent to the CMP protocol that is defined in SE that we've seen in the earlier talk. Okay. Now the RSU can detect this vehicle and can associate it with the message sending from this vehicle, so it knows that, okay, this is the Eagle vehicle. All right, and then we start to see. So the driver is approaching the axis of the road, and we can see that here the car is approaching. Now, if we pause here, there are two cars approaching this sort of T intersection. And the RSU, it has a camera that monitors the two sides of the road. And it has a processor to do computer vision and vehicle detection and tracking, so that it can start tracking those vehicles and then send the information to the Eagle vehicle. Now, it's important to keep in mind that the two vehicles that is approaching the road doesn't have any CV2X modem at all. So you can think of this as like an early deployment of CV2X, where you don't have a lot of penetration rate. It's just like this one guy, Eagle car, and the RSU that have this capability. But thankfully, because the RSU have this smart capability, then it can still detect other vehicle that doesn't have the communication capability. So it can detect these two guys approaching. Now this car is approaching very closely to the T intersection. Then it can become dangerous to this vehicle who is also approached the intersection, and the vision is blocked between these two guys, right? So they cannot see each other. Then because of these, the RSU start flagging these two approaching vehicle as dangerous, and then issue a stop warning to the ego vehicle. Right. And thanks to that, the driver sort of stopped right here and see the two cars passing by. And then after that, he safely make the safe turn. Okay. So now this scenario turned out to be quite nice for the driver who maybe, after a long day of work, being so hurried to get home, without the early warning, maybe he may have to pay quite a big bill in terms of car repayments. Okay. All right. So this is the first scenario. Now let's go to the second scenario, okay, so I've explained before that this is the case where we use an RSU to augment not augment, but replace GNSS signal completely, because here in this case, the GNSS signal is completely lost. And then if you think about it, like when you have GNSS, right, which means you have connection to the GNSS satellites, and not just a single connection. Like you have to be able to detect at least 3 or more satellites. Like 3 is the minimum. But normally you need more to have like a good fix of GPS signal or GNSS signal. All right. Now, if you want to replace GNSS, you have to have as many. I mean, without, let's say, advanced hardware and stuff, you need at least 3 or more of such RSU to provide the same kind of signal, right? Of course, if you say you can do, an angle of arrival detection and so on, but that requires a lot of hardware. Like you have to have more antenna, which is, to be honest, there's not a lot of real estate in the car to have that many antennas, right? So then the nice thing about this scenario is that we only use one RSU. And then we show that with that only one RSU, you can provide good enough, quite accurate positioning to the car. And then the second nice thing about this scenario is that for positioning, normally we talk about, let's say, millimeter wave or radar type of positioning, because there you have more bandwidth and then you have more resolution of the positioning. But here, but that is not a given, right? Because millimeter wave or radar is like it's more hardware. So here we are using only a like typical sub-6 gigahertz frequency kind of signal, and we show that we can still achieve good enough, let's say, within meter of accuracy for the vehicle, which is not bad. It's not like equivalent to radar. It's not bad for sub-6. And given that their spectrum, for example, the unlicensed spectrum is available at 5 to 5.9 gigahertz, that can easily give you more than 100 megahertz of signal. That's not a bad deal, basically. Right. Okay, so then with further ado, let's go into the video. Okay, so let me just explain what is the layout here. So we have, so maybe we still remember the headquarters building, which is now here. And then now this is the parking lot on the left that we see in the earlier video. And now there's also a parking lot on the side. And then we have a car that is right here next to the RSU, and it's about to enter this parking lot. And then this is captured in this video. Like we have a camera at the other side of the corner that overview this setting. On this screen is the positioning error monitoring. And now we have 3 types of positioning. So we have ground truth. Let's say somehow we can know exactly where the car is. It's the ground truth. Now, is dead reckoning? What is dead reckoning? So basically, for vehicle, we know vehicles are mechanical devices, and they move fast, which means that their movement is it's not like some Brownian movement that, you know, it just jump here and there in a very drastic motion, like go into curves, smooth curves. And then there's a lot of sensor in the car to capture that movement, like accelerator and, you know, gyroscope and everything, and that can track this movement. And then we can use that to estimate, like, let's say, you know, a location of the vehicle in the past, you can use those information to keep on tracking the position of the vehicle in the future, even when you lost the GPS completely. And that is not something new. That's people have been doing that from, I don't know, from 1986. That is called dead reckoning. And now we have fusion, which is what the solution is doing. So basically, we leverage that fact and say that, hey, once you have this dead reckoning, you don't need that many of RSU. You just need one RSU to provide the relative position from the car to the vehicle, and then you can fuse that with dead reckoning data, and then you can get pretty good positioning location. And that is what we are about to see here. Okay, so now we start the demo. And now the vehicle is connected to the RSU, and now it starts entering the garage. Once it starts entering the garage, it's lost GPS. And then the fusion just also stopped, you know, maybe we should go back a little bit. So here, by this point, it's lost connection to the RSU. So then the fusion stopped working completely. So now you can only see the dead reckoning. So it drive in the garage for a while, and now it start getting out of the garage. Now you can see that the dead reckoning, because, you know, nothing is perfect, and then you completely lost GNSS, so things start creeping. And after a while, the dead reckoning is way far from the ground truth. Okay, but then here, remember, this is the point where you start seeing the RSU again. Now, once you start seeing the RSU again, there's a connection, and then you start doing the fusion, and then with fusion, you can see that the accuracy start up right here, which is pretty good, right? Why the dead reckoning keep being drift away. And then you can start get a pretty good position. Once you get out, then the accuracy is very good, right? And meanwhile, the dead reckoning keep, you know, now start readjusting their position because they start seeing GNSS. And then after a while, it's converged to the. So here, right, you can see that if you just rely on dead reckoning and GPS, you have this critical moment where your tracking positioning is way off. And that can cause you that problem when, you know, your map suddenly just reoriented crazily, and then you make the wrong turn. And now we just showed that with just one RSU, you can completely avoid that problem. Okay. And then here in the monitoring, you can see that the positioning error here, when in this trajectory, like the dead reckoning positioning error is all the way to 14 meters. While if you have the fusion of, you know, positioning with RSU aided signaling, then we start off at 6 meters and then converge quickly to below 1 meter after a while. Okay. Now this is the last demo that I would like to show. So this is about radar. So as I said before, radar is great until everyone has radar. And this is exactly the case. Let's first start with this case first. So you have one stop vehicle here at this corner of the Z, which is the target we want to detect. We have an Eagle vehicle that is equipped with a radar that is currently pointing to this direction. And we have these two guys that are interfering vehicle that keep driving toward, right? Now everyone start moving. Here is the dash cam from the Eagle vehicle point of view. Right. So now let's say we do nothing. Just take radar on the off the cell and let everything run. Let's see what happens. So here you can see the Eagle radar output here. So basically, this is a reflection map on the field of view, where the brighter the points, the more energy are there, which indicate that there's a target. And the darker the point, the less energy is concentrated there, which means there's no target. So in this case, because the car is moving toward the world, and you can see that all these parts is illuminated. Right. And then one is make the turn, then this part is not illuminated anymore. Now you can start seeing some target here, which is probably this guy over here. Okay, so now here's the point. So because you have interference, so now suddenly you see a lot of this bright patch of signal here that you cannot tell whether it's a target or anything, okay? Which is basically what the interference does to your radar receiver. So you can tell that there's some interference approaching you. Let's go back for a while. By the fact that there's some circle here that keep approaching you. But once that circle approaching you is close enough, then something else happens. Like you see this, the screen is bright all over the places. And then you cannot detect anything at all until the interference passes. Then you can see this target at around 50 meters away. In some cases, reduce the time that the radar system gives to the driver to react to possible crashing scenario. Right. So maybe one of the highlights that I would like to make after this is not interference is bad for the radar receiver, but it's bad in two ways. It's either create a ghost target, which means that it's not real target. It's just because either it's transmitting some blocking signal to you, then it's appeared to be as a target. So it's a ghost target. Or it can jam your radar receiver that you cannot receive any target that masks the real target. So that is two ways that interference works. Right. Okay. Now in this case, let's say we do some cooperation. Let's forget about a minute about how we do the cooperation, but let's say there's some cooperation. For simplicity, we have a 5G connection that connected to the base station, and then the base station, the cloud can do the job of the coordinator between vehicles. Now, this is just for simplicity in this setting, but theoretically you can do it with anything. Like you can have an RSU, like a lamppost right there, where you have an RSU, and the RSU receive the cycling communication from those vehicles, and then talk to those vehicles to do the coordination. That can also be the case. And then we will see that once we start doing coordination, things start to become better. Okay, so now you can see that your screen is not being blocked anymore. Right? And then you can still start to detect the target from about 120 meters away, with compared to earlier, it's just 50 meters away. So it's more than 200, more than 2 times of improvement in terms of detection range. So now what is the coordination? Let's say, without going to the detail, what does coordination look like? Let's first analyze the situation, right? So we know that interference acts in 2 ways. Either it creates this thermal noise, which is a blocking, or it creates a ghost target. Now, one way to overcome interference is to avoid interference. But avoid interference will come with a cost. Like, the only way that you can avoid interference is to use orthogonal resource for different radar, which means that either you can FDM or TDM. If you are doing TDM, then basically you are reducing the frequency that the radar sample can be generated, and also reduce the maximum range that you can detect. If you are doing FDM, then basically you're reducing the bandwidth, and that sort of reduce the resolution of the measurement. So all those things, even though they are feasible in principle, but it comes with a cost, right? Now let's say if we cannot avoid interference, then why not control it so that it appear in a known, it have a known characteristic, because you control things, you can make it as a known characteristic. And then from the radar side, you're not just doing object detection, right? We also, after the object detection, there will be a phase of filtering the object anyway. So then if something that we know to be interference, then we can just filter that out in the process of tracking the object. And that is exactly what we're doing here. So maybe let me rewind the video a bit so that we can see the case of cooperating, right? Again. Okay. So now with cooperating, now what we can see is that you don't start, let's say here. Here we still see this random flashing of bright red, right? Here, which means that we are controlling the interference in the way that the ghost target is appearing as a random object, right? So basically, it's like, okay, one moment is here, the other moment it jumps to the other place. And we know, right? We already seen in the last video, like car or vehicle or object on the road are not those kind of things. They are not subatomic particle, right? They move in a very smooth way. So then anytime that you see those things that happen, you can safely ignore them and say, okay, this is the ghost target. And then you can see that now, even as the car approach each other, earlier when the car approach each other, the whole screen go bright. Now the whole screen doesn't go bright, but it's just like one part of the screen, like this circle is extremely light. This is the ghost target in close proximity. The rest is still normal. So maybe when this happens, you may lose the target in a frame or two, but then once you do the tracking, that single frame or two doesn't matter that much, right? And then you can start seeing the target from here. So that is basically the idea. So if we compare with, let's say in this case, for example, let's fast forward a little bit, maybe a little bit more, right? Here we can see the difference between the two cases. See, when without coordination here, when these two guys are very close by, the whole screen go red, and then you cannot see anything for a long period of time. And same thing with the next car. Yes, so then basically that is it for my presentation. So to recap, here in Qualcomm we envision that CV2X is not just a technology, it's not just like a wireless communication technology, but it's an enabler of a lot of transportation application. So that it's not sufficient to just go on and deploy a communication technology. You have to define the standard application to run on it, and then you also have to develop the how to say, at least in this case, I would love to say it's a non-killer app, like the application that give benefit for everyone on the road, so that people have an incentive and go on and deploy and buy the device and then enjoy the benefit. And we are working very hard on that front And these 3 demos are the example of what we have been achieving so far in this year in this effort. And all these demos are was shown in MWC in Barcelona, and there's a nice video on YouTube that I will put a link in the abstract. And if people is interested in seeing that, then please go ahead and check the video out. Thank you very much for your attention today.
Thank you very much. Very nice presentation, very nice work with a lot of applications, hard work, things that work. That's surprising somehow. Surprising also to see how technologies like radars that's supposed to be dominated by us since decades keep giving us some surprise. So,
thank you.
Any question, Francois? I see Francois, please.
Yeah, so thank you, Tien. It was a very beautiful lecture. I have a question on which is a bit orthogonal about the legal aspects. I mean, so this chipset, assume I buy this chipset and I install it in my car, and there is an accident. I mean, what happens? I mean, so is it like I mean, when you use Google Map, I mean, so you use it, but is there like are these legal aspects taken care in whatever contract that you have with customers? How does it work? It's just since there is really a safety issue, how do people handle these type of questions?
Okay, so you mean to clarify the question, Francois? So when you say chipset, do you mean the communication chipset, or for example, in this case, the or positional chipset or radar chipset?
Well, for instance, I mean, you alluded to this protection of vulnerable bicycle or bike, and or pedestrian, and assume, I mean, I mean, I don't know how the warning works, and so I'm just curious, I mean, about this legal aspects.
Yeah, right. So it's communication chipset. Okay, so then that is a very great question. Actually, I'm also not very clear about the legal aspect. By all means, I'm not working on legal, but my speculation is that the chipset is doing the communication, right? So then it's just convey what is being sent to the pipe. So it's what being sent to the pipe and what is the action being taken on the information that is really matter. But then the chipset is only have a fault when it's failed to deliver the packet, right? So then maybe in terms of legal, it's not a clear yes and no question, right? It depends on where the failure is. Let's say if the application is good, which means like the action is good, but the information is not good. Let's say, this object is being detected by a computer vision component of a car, and that the seller of that computer vision make a mistake, for example. Then maybe from legal point of view, that is the people who installed, who developed that computer vision model have the liability. Or let's say if the autonomous car who take action on that information have some faulty logic, then that is the liabilities on the car. Or maybe they're gonna take a holistic approach and say, okay, whoever, like say, sell the cars had to be able to test and then take the full liability for the whole thing, because anyway, they are the one who benefit from the selling of the car, and they provide the service for the user, so they should be the one who take the liability. So I don't know, actually. Those are the few speculative answers that I can come up with.
Thank you.
Any other question, maybe online? Nothing. I have a doubt about what is the standardization framework for who should run the computing, where, which kind of chipset can be used. Is it something which is already under standardization? I mean, I understand the V2X is there, but all There's a lot of more than that. Yeah.
You mean from the coexistence point of view, or from the?
For instance, for cooperation.
For cooperation.
Cooperation, is it enough to have standard C V2X, or in computing at least?
So you mean for cooperation between? Okay, so my understanding of the question is that assume that you have different type of let's say radio access technology on the road. Let's say DSRC and CV2X and maybe something else, right? And they all do car-to-car communication. Then the question is how these different kind of car can connect to each other.
Right, but the question is also how do they connect the radio parts, the communication part to the computing part? Because the computing is up to who? The computing, when you have a cooperative protocol like the one that you show, who is in charge of doing the cooperation? Each car independently, or I mean, is there any standard framework to do that, or everyone is left free to do whatever he wants with the data that he gathers?
So at least in this example, the network is taking charge of this, because it's anyway an early prototype. But that doesn't preclude a solution. Let's say locally you have a car that's doing coordinated to other cars, or let's say a certain, or let's say the ego car, for its own interest, can broadcast its coordination characteristic to other people. And if you receive that thing from everybody, then everybody understand each other, and they can work with each other. Right. All I can say is that it's a bit early to talk about standardization right now, because the standardization has to come in due course anyway. Let's say we demo this solution, and then let's say people in the industry and everything like it, then the standardization can start, right? We can go on to, for example, SAE. So basically, if this automotive application, we can think of like SAE is the organization in the US. In China, you have CSAE. And I think in Europe, most of the thing is happening in SC. And then they will go on, define what is the packet format and so on. Normally in automotive area, I don't see a lot of people trying to mandate a certain solution, because the car OEM tend to prefer to use their own solution, like proprietary solution.
Right. Okay, thank you. So if there's no other question, I think we can stop here. Thanks to the speaker again.
Yeah, thank you.